remember the technique, take the equation and write the solution as y1 times u, and then just go on. But you'll find out that you go through the same steps over and over again, and it would be great if we could just solve a second order equation in one sweep and then use that as reference. And that's what we're going to do now. Okay? Let me just write it in I have a certain canonical form over here. Okay? And you have to be very, very careful. A lot of students make mistakes on this. You know, there's certain, when you have a formula, there's always certain hypothesis that goes behind that. The equation has to be of a certain form. And I'll kind of give you the warning that happens over here. Okay? Let's start off with the most general second order linear equation. What would that be? Of order 2. It would be a2 of x, y double prime, plus a1 of x, y prime, plus a0 of x, y equals 0. Okay? So, for n equal to 2, I think my pen's going to run out over here. Hopefully the red has something. Okay, n equal to 2. What's going to happen? It's going to be L on y is going to be a sub 2 of x times the second order y respect to x plus a1 of x dy dx plus a0 of x y is equal to 0. Okay? Now the formula I'm going to derive assumes that the coefficient of y double prime equals 1, but you always can do that, right? Just divide through by a2. So there's no loss of generality of assuming we're going to start right away with a differential equation where the coefficient of y double prime is equal to 1. And I'm just using the notation in the book. They write it as the second order of y with respect to x. And they call it, there's other ways, the ratio of a1 to a2. Just call that p of x. dy dx. Write out the derivative explicitly. Plus q of x times y is equal to 0. Okay, so you have to remember that when we're going to, there's going to be a lot of blackboard taken up, and I'm going to have a formula at the end, and I'll put a box around it. When you use this equation, the formula that we're going to derive, you have to remember to put the equation in this form, because that's the starting point of this whole thing. Okay, so there's our second order differential equation, and suppose, again, by inspection or by physical arguments, suppose y1 of x is a solution of the homogeneous equation, right? Plug in y1, and that solves it. The great thing now about reduction of order is what's going to happen. Okay, we know what's going to happen. We're going to plug in the substitution like we did before, let y equals y1 times u, and what should happen, okay, because of the theory I did before, is that if we don't make a mistake in the algebra, even in the general case, the coefficient of u of x should go to 0. Then we'll have an equation that has u prime to u double prime. We'll let u prime equal v. It's a first order linear. You know how to do first order linear. So now it's just a matter of you do the integrations. But in theory, it can always be done. So now we make the substitution, let y of x equal this homogeneous solution, y1 of x times u. And remember, at this stage, you know y1 of x. Okay, someone gives it to you, or by inspection, you're able to determine one of the solutions of the homogeneous equation. So y1 of x is not known. So this is like a change of dependent variable from y to u. And now we're going to basically just crank out the derivatives over here. So what's dy dx? Using the product rule, it's going to be y1 prime of x times u plus y1 du dx. Okay? Let's do the second derivative of y with respect to x. We're going to get y1 double primed times u, right? Follow me, make sure I don't make a mistake. And then y1 prime u prime, I picked that up twice, to y1 primed du dx, plus y1 second derivative of u with respect to x. Let's check that again. y1 double prime u, y1 prime u prime, y1 double prime. Okay, now we have all our derivatives. Let's just plug into the equation and see what happens. Okay, what's L operating on y now? I need the second derivative. Let me write it in terms of, I'm just going to rearrange this to get the higher derivatives first. I have y1 second derivative of u with respect to x. 2y1 prime u prime. and then y1 double prime u. Okay? So that's the first term. Now we need p of x times the first derivative. What do we have for dy dx? We have two terms. We have y1 du dx plus y1 prime du. P of x times dy dx, y1 prime du plus y1 du dx. Okay, and now q of x times y. And y is simply y1 of x times u. Okay, that's L on y. Let's get all the stuff together, get all the u double primes together, the u primes and the u's, and see what happens. We find that L operating on y, there's only one term involving the second derivative of u, that's just this guy over here. y1 second derivative of u with respect to x. Plus, now let's look at all the coefficients of dy dx, of du dx rather. I have a 2y1 primed over here, right? 2y1 prime du dx. Plus p of x y1 right? That's the du dx stuff. And now let's collect all the stuff that has u on it. Okay, and we know by reduction. Why am I doing it this way? Because I know from my theory for reduction of order that the coefficient of u has to go to 0. So that's what motivates me to put all the u double primes together and all the u primes, etc. Okay, let's see what we have multiplying u. Okay. I got a y1 double primed over here, right? Y double prime times u. P of x y1 prime times u plus q of x y1. That whole thing's multiplying u. Okay, we saw in the general theory that the coefficient of u should come out to be 0. And I think you can see that. What's the thing in brackets? Isn't that just L on y1, right? Remember how we started. Suppose y1 of x is a solution. What does that mean? y1 double prime plus p of x y1 prime plus q of x y1 equals 0. That's exactly what's in that last bracket. So this last bracket over here, multiplying u, is L on y1, and that's 0 by given, right? It's a solution of homogeneous equation. So now the equation reduces down just to the first two terms. Let's see what we can do with that. So the differential equation that I have to solve now is going to be y1 of x, which is known, times the second derivative of u with respect to x, right? And then I have this combination over here, 2y1 prime of x plus p of x y1 times du dx equals 0. y1 u double prime, 2 prime, p of x y1 equals 0. Let's divide, we can divide by 1 and do the same things I did before. Let v equal du dx. So you'll see that's a first order equation on v. Okay? And let's divide through by y1 also. This becomes the second derivative of u with respect to x, and by this introduction, it's just dv dx, right? Plus 2y1 primed of x divided by y1, right? Divided by y1. And luckily over there it just cancels, plus p of x times v is equal to 0. Okay, so I divide through by y1, and I just let du dx equal v. Okay, you see it's separable. Right? Differential of v divided by v plus 2y1 prime of x divided by y1 of x plus p of x dx is equal to 0. Now we're going to integrate, okay? So nothing you can do with this thing because p of x is just p of x. There's no way you can do the integral p of x in general, unless, right? But once you have a concrete differential equation, you'll know p of x, so you can do that. Yeah?
What is that supposed to be in this little section here? 2y1 prime?
Primed over y1.
No, top.
Here?
Top. top shelf.
Over here?
Yeah.
Okay, what we did over here, we got to this point, that's okay?
I can't read what that says.
Okay,
Y1
it says
prime,
y1
but-
u double primed
Okay.
plus bracket 2y1 primed plus p of x y1. What's that, should I write it a little more neatly? Is that the problem?
Yeah, that, I have
Two
no idea what
Y1
that is.
prime.
Looks like an infinity symbol to me.
y1 prime of x. Okay? Take this.
Okay.
Okay?
Yeah.
Get my handwriting. Don't hesitate to say, hey, I can't read it. Okay,
Yeah.
so now we get down to here. Now, you'd say, oh, what's this integral of y1 prime over y1? Do I have to leave it in integral form like that? But you don't. Because a little trick over here, what's with respect to x of the natural log of y1? Isn't that just 1 over y1 prime? By the, right? You're going to differentiate and use the chain rule. And that's exactly what I have over here. I got y1 primed over y1, right? And then 2 in there, so therefore the integral of that is just 2 log y1, okay? So now let's integrate. The integral of 1 over v dv, that's just a log of v. And again, I emphasize again, you've got to know your laws of logarithms. What would be the integral of 2y1 primed over y1 will be 2 times this integral, which according to that is 2 times the log of y1, but 2 log y1 is the log of y1 squared. Okay, so we actually can do that integral. It's a perfect derivative, so to speak. It's just 2d by dx of log y1. And this thing, of course, we just have to leave the indefinite integral of p of x dx. And again, I'm going to make things simple, and instead of putting arbitrary constant, put equal to 0, because I don't need the most general solution here. I just need a solution to get my second independent solution. And now we use properties of logs, okay? This becomes the log of what? V y1 squared equals, be careful now, minus the integral of p of x dx. And again, I remind you that when you start any problem, you'll know the coefficients. So you know p of x, you know q of x. Comes out that q of x doesn't even enter into this final formula. Very interesting. But you do have to know p of x, and therefore, if we know p of x, hopefully I can do that integral and get that explicitly as a function of x. Okay, let's go one more step. If the log of vy1 squared is equal to that, by the definition of logarithms, vy1 squared is simply the exponential of the right-hand side, minus the integral of p of x dx. Okay. And then finally, I can solve for v of x. Divide by y1 squared. I get 1 over y1 squared of x, which I know. See, everything on the right-hand side is known. Exponential of minus the integral of p of x dx. One more step and we're finished. We have to get u, right? Because the solution was u times y1. So let's get u, multiplied by y1, and then we have our second solution. See, what would happen basically is that if you didn't have this formula, then every time you do a second order equation, you're essentially going through this over and over again every time. So it's nice to just have a formula at the end. So the last one says v is equal to that, but remember the substitution. Where did I do that? Here. I let v equal to u dx. So now I have the derivative of u with respect to x is this guy over here. 1 over y1 squared, which is a known function of x, exponential of minus the integral of p of x dx. And then we integrate that finally to get u of x. Is the integral of 1 over y1 squared exponential, I told you it's going to be a mess at the end, the integral of p of x dx. Final step, okay, what's the second solution? When we started this whole thing, we said let the second solution be of the form y1 times u. And I'll put a little subscript on that, y2, to remind you it's the second independent solution. So the second independent solution, y is 2 of x, is given by y1 times u. y1 of x, which you know, right, Then we have the integral of 1 over y1 squared of x, which you know, exponential of minus the integral of p of x dx, dx. Okay? Let's put just a box around this. Okay, this is the final equation, or the final solution, right? Okay. So, forgetting all the intermediate steps, let's see, how we're gonna apply this. So we have a differential equation of second order. Notice this works even for variable coefficients. Okay? This is the most general second order linear equation, homogeneous, that you can write. Be sure to base the coefficient of y double prime equal to 1 by dividing through. That's what most students forget to get. That would give you your p of x, right? Okay. The problem will be stated as y1 of x is a homogeneous solution. And again, in practice, you can get that many times just by inspection and knowing the physics of the problem. So we have one homogeneous solution, but the second one is not so easy to see. This formula will tell you what the second solution is. You identify p of x, you have that right over there, right? You integrate it, put a minus, hit it with an exponential, divide by y1 squared, do the integral, multiply by y1, and that's the second solution. Let's take the first problem that we did, where we did it without the formula, apply the formula, and we should get the same answer, right? Let's go back to example number 1 again. That equation was y double prime minus y is equal to 0, okay? So it's already in the form that we want. Y double prime, the p of x is equal to 0 over here, right? And q of x is equal to -1. Everybody see that? Because the p of x is the coefficient of dy dx. So here, p of x is identically 0. Okay? So let's plug in, and remember the first solution, that was y1 of x, in this case, was e dx, I believe, right? E dx. Yep. Okay? So, according to our formula now, the second solution, okay, is given by the following. Take the first solution, which in this case is e dx, multiply that by the integral. What's 1 over y1 squared? That's e to the minus 2x.